Lake Tahoe can look still enough to read the shoreline in its reflection, yet beneath that calm surface lies one of the basin's most consequential geologic structures. The West Tahoe Dollar Point fault system has drawn sustained attention because it sits in the western part of the lake basin, extends through or beneath some of the most closely watched shoreline segments, and has been tied in published studies to a quake large enough to reshape the region. How much strain can a fault carry before it releases? What does a rupture mean when it happens under more than 500 meters of water? And why has a place known for recreation, tourism, and year-round quiet remained on seismic watch for decades? The basic geography is part of the reason the fault matters. Lake Tahoe straddles the California-Nevada border, and the basin is not a random bowl of water, but a tectonic depression bounded by active faults on multiple sides. The West Tahoe Dollar Point fault zone runs along the west side of the basin, continues beneath parts of the lake floor, and has been described in regional planning and scientific summaries as one of the major active fault systems in the Tahoe area. It is not an isolated crack in the ground, it is part of a broader network that includes the North Tahoe and Incline Village systems, all of them capable of producing strong shaking. The most attention-grabbing estimate linked to this fault is the possibility of a magnitude 7.3 earthquake. That number comes from the Scripps lead work summarized in 2009, which concluded that the rupture geometry and observed offset supported an upper limit of magnitude 7.3 for the basin's most dangerous fault. The same summary noted a fault length of more than 50 kilometers, or about 31 miles, and a slip rate approaching 0.8 millimeters per year, suggesting a structure that has been moving slowly but persistently over geologic time. That magnitude estimate did not appear in a vacuum. The published work that fed it used high-resolution seismic imaging and lake-bottom coring to reconstruct deformation along the fault, especially in Fallen Leaf Lake and Lake Tahoe itself. The findings pointed to repeated displacement in young lake sediments, a fault that cuts through late quaternary deposits, and an event history that was not confined to a single isolated rupture. In other words, the fault's behavior was read from the sedimentary record, not guessed from surface cracks. What makes the West Tahoe Dollar Point fault especially consequential is that it is tied to a lake basin with deep water overhead. Scripps noted that Lake Tahoe is more than 501 meters, or 1,645 feet, deep. When a large fault rupture occurs under or near a body of water that deep, the vertical displacement can move huge volumes of water and generate waves along the shoreline. That concern is not theoretical in the way casual speculation is theoretical. It is a hazard mechanism that has been studied in the basin for years. Regional summaries have described tsunami or seiche waves in the 3 to 10 meter range, with some older planning documents citing potential waves of about 30 feet, or roughly 9 meters. The fault's geometry helps explain why it has remained in the hazard conversation. USGS fault database material describes the related Tahoe Basin faults as steep, bathymetrically expressed structures with scarps beneath the lake floor and evidence of recurrent quaternary movement. The mapped traces are not always sharp on land, but offshore they show abrupt slope breaks and offset sediments. That matters because a fault that has repeatedly displaced recent deposits has already demonstrated that it is not fully dormant. Regional planning material has long treated the Western Tahoe fault system as a serious hazard source. In one planning summary, the West Tahoe Dollar Point fault was identified as the longest of the major Tahoe Basin faults, extending across the basin on a north-south trend. Another regional summary described the west side faults as capable of large ruptures and linked them to possible lake waves that could affect the shoreline. This is why the fault repeatedly appears in hazard mitigation documents, shoreline planning, and seismic background sections for projects around the lake. The age of the last major event is central to the question of risk. The Scripps summary said the West Tahoe fault last ruptured between 4,100 and 4,500 years ago. The same summary placed the characteristic earthquake cycle for the basin at roughly 2,000 to 3,000 years for a magnitude 7 event. Even without turning those numbers into a prediction, the interval between the last known large rupture and the present day is long enough to keep the fault on every serious regional hazard list. The recurrence issue is one reason the region's planners continue to reference the fault in official documents. A draft hazard mitigation plan for the Tahoe region repeated the script's finding that a magnitude 7.0 plus earthquake occurs every 2,000 to 3,000 years in the basin, and that the West Tahoe Dollar Point fault appears to have last ruptured more than 4,000 years ago. Such language does not mean a quake is imminent, but it does mean the basin cannot be treated as seismically quiet. The shape of the lake floor makes the hazard more complex than simple shaking alone. The western shore drops off into steep underwater relief, and the fault zone is associated with sharp scarp-like features on the basin floor. USGS fault records note that the larger Tahoe Basin faults are expressed by abrupt changes in slope and offset lake sediments, while the script's work link the geometry to the potential for tsunami generation. A rupture in that setting would not only shake buildings and infrastructure, it would also have the capacity to move water in ways that can amplify shoreline damage. That is why the fault has become the focal point when Lake Tahoe's seismic hazard is discussed in public planning material. The basin does not rely on one line of weakness, but the West Tahoe Dollar Point system stands out because of its length, its offshore reach, its slip history, and its position relative to populated shoreline communities. The concern is not abstract. Homes, roads, marinas, and utility corridors are concentrated around the very rim that could feel both strong ground motion and water movement from a large event. The scientific record also shows that the fault's current reputation was built over time. Early mapping recognized active deformation along the basin margins. Later seismic reflection surveys revealed fault scarps under the lake. Then high-resolution imaging and coring narrowed the timing of the last large rupture and improved estimates of slip rate and fault length. By the time the 2009 studies were summarized publicly, the West Tahoe fault was no longer just a line on a map. It had become a measured, dated, and repeatedly analyzed seismic source. Even so, the fault remains less precisely constrained than people often assume. The USGS fault database entry for the Tahoe Basin stresses that some offshore fault locations are poorly constrained because much of the mapping depends on high-resolution bathymetry and seismic interpretation. That does not weaken the hazard, it simply means the exact trace can be harder to pin down than a surface fault scarp on dry land. In practical terms, the uncertainty is not about whether the basin has active faults. It is about the fine-scale geometry of where the rupture would break through and how the movement might distribute itself across related traces. A fault capable of producing a magnitude 7.3 earthquake is not defined by a single parameter, but by a combination of length, geometry, accumulated strain, and the mechanical properties of the surrounding crust. The West Tahoe Dollar Point fault meets those conditions in ways that are consistent with other large normal faults along the eastern margin of the Sierra Nevada. Its north to south orientation follows the broader tectonic regime of extension in the Basin and Range Province, where the crust is being pulled apart at a slow but persistent rate. That extension is not uniform. It localizes along faults that accommodate displacement in discrete increments, sometimes separated by thousands of years. In Lake Tahoe, that process is expressed in the form of a down-dropped basin bordered by uplifted blocks. The west side of the basin, where the West Tahoe Dollar Point fault is located, acts as one of the principal structural boundaries. Over time, repeated motion along the fault has helped deepen the basin, contributing to the lake's current depth of more than 1,645 feet, or about 501 meters. Each significant rupture has likely produced a measurable vertical displacement, even if the individual offsets were modest when compared to the full depth of the basin. The slip rate of approximately 0.8 millimeters per year may appear negligible at first glance, yet over a span of several thousand years, it translates into accumulated strain that must eventually be released. Unlike a continuous, steady movement, the fault remains locked for long intervals, storing elastic energy in the surrounding rock. When the stress exceeds the strength of the fault, that stored energy is released in a sudden rupture. The magnitude of the earthquake depends on how much of the fault surface breaks at once, how far it slips, and how efficiently the rupture propagates along the fault plane. Evidence from sediment cores extracted beneath Lake Tahoe indicates that the fault has ruptured multiple times in the late Quaternary period. Layers of disturbed sediment, offset strata, and abrupt changes in deposition patterns all point to episodes of rapid displacement. These features serve as a geological archive, preserving the timing and relative size of past events. While the record does not capture every rupture with perfect clarity, it provides enough resolution to establish a pattern of significant earthquakes recurring over multi-thousand-year intervals. One of the more complex aspects of the West Tahoe Dollar Point fault is its segmentation. It is not a perfectly continuous line but a system of linked segments that may rupture together or independently. In some earthquake scenarios, a rupture might be confined to a portion of the fault, producing a smaller magnitude event. In others, multiple segments could fail in sequence or near simultaneously, generating a larger earthquake closer to the upper magnitude estimate. This variability complicates hazard assessment because it introduces a range of possible outcomes rather than a single deterministic scenario. The interaction between the West Tahoe Dollar Point fault and adjacent fault systems adds another layer of uncertainty. The Tahoe Basin includes several active structures, and stress changes on one fault can influence the likelihood of rupture on another. A significant earthquake on a neighboring fault could redistribute stress in a way that either delays or advances failure on the west side system. This interconnected behavior is typical of fault networks in extensional tectonic settings, where multiple structures share the burden of accommodating regional strain. Ground shaking from a magnitude 7.3 event in the Lake Tahoe Basin would be expected to be strong across a wide area. The intensity would depend on distance from the rupture, local soil conditions, and basin effects that can amplify seismic waves. Sediment-filled basins are known to trap and reverberate seismic energy, prolonging shaking and increasing its impact on structures. In the Tahoe region, variations in sediment thickness and composition could lead to uneven distribution of shaking intensity, with some areas experiencing significantly stronger motion than others. The presence of steep underwater slopes along the western margin of the lake introduces the potential for submarine landslides triggered by strong shaking. When sediment on these slopes becomes unstable, it can fail and move downslope, displacing water in the process. This mechanism is one of the primary ways that earthquake-generated waves can form in enclosed or semi-enclosed bodies of water. In Lake Tahoe, such displacement could produce waves that radiate outward toward the shoreline, affecting multiple areas around the basin. Wave behavior in a lake differs from that in an open ocean, but the underlying physics of displacement and propagation remains the same. A sudden vertical movement of the lake floor or a large landslide can generate waves that travel across the basin and reflect off the shoreline. Depending on the shape of the basin and the location of the disturbance, these waves can interfere constructively, leading to localized amplification. This means that some shoreline segments could experience higher wave run-up than others, even if they are at similar distances from the source. Historical records in the Tahoe region do not include a modern example of a large basin-wide earthquake of this magnitude, which limits direct observation of such effects. However, geological evidence of past disturbances, including disrupted sediment layers and shoreline features, suggests that significant events have occurred in the distant past. These records provide indirect confirmation that the basin has experienced strong shaking and associated water movement, even if those events predate written history. Infrastructure around Lake Tahoe has expanded significantly over the past century, increasing the potential consequences of a major earthquake. Roads, bridges, utility lines, and residential developments are concentrated along the shoreline and in nearby communities. Many of these structures were not originally designed with a magnitude 7.3 earthquake in mind, particularly older buildings constructed before modern seismic codes were adopted. Retrofitting efforts have improved resilience in some areas, but the overall exposure remains substantial. Transportation corridors are a specific point of concern. Highways that trace the lake's edge are vulnerable not only to ground shaking, but also to slope failures and rockfalls triggered by seismic activity. In steep terrain, even moderate shaking can dislodge rocks and destabilize slopes, leading to blockages that isolate communities. In a large event, multiple segments of roadway could be affected simultaneously, complicating emergency response and evacuation efforts. Utilities such as water supply, wastewater systems, and electrical distribution networks also face risk. Pipelines that cross fault zones can be damaged by ground displacement, while treatment facilities located near the shoreline may be exposed to both shaking and wave action. Power infrastructure, including transmission lines and substations, can be disrupted by both direct damage and cascading failures within the grid. The interconnected nature of these systems means that localized damage can have broader regional effects. Emergency response planning in the Tahoe Basin takes into account the possibility of a large earthquake, but the unique combination of hazards presents challenges. Access routes into and out of the basin are limited by geography, and heavy reliance on a small number of highways can create bottlenecks. Communication systems may be strained or disrupted, particularly if power outages occur. Coordinating response across state lines adds another layer of complexity, as the basin spans both California and Nevada. Public awareness of the West Tahoe Dollar Point fault has increased over time, largely due to the dissemination of scientific findings and their incorporation into regional planning documents. The identification of a specific fault with a defined magnitude potential tends to focus attention in a way that more generalized hazard descriptions do not. At the same time, the absence of recent large earthquakes can create a perception of safety that does not fully reflect the long-term behavior of the fault system. Seismic monitoring in the region continues to improve, with networks of instruments capable of detecting small earthquakes and tracking patterns of activity. These data help refine understanding of how strain is accumulating and how smaller events are distributed across the fault network. While such monitoring cannot predict the exact timing of a large earthquake, it contributes to a more detailed picture of the basin's seismic state and informs updates to hazard models. The broader tectonic setting ensures that the processes driving the West Tahoe Dollar Point fault will persist. The extension of the crust in this part of the western United States is ongoing, and faults within the Basin and Range Province will continue to accommodate that deformation. The Tahoe Basin, with its deep water and well-defined fault boundaries, remains one of the clearer expressions of that tectonic activity. Over long timescales measured in thousands of years, the accumulation and release of strain along faults like the West Tahoe Dollar Point system is an expected part of the region's geologic evolution. The combination of fault mechanics, basin geometry, and human development defines the hazard profile. A magnitude 7.3 earthquake would not be an isolated physical event, but a complex sequence involving rupture propagation, ground shaking, potential landslides, and water displacement. Each component interacts with the others, shaping the overall impact. Understanding that interplay is central to assessing risk in a place where the landscape itself records the history of past earthquakes, while continuing to evolve under the same forces.